Alright class, what we're going to talk about today is bond enthalpies. And the main thing is we have reactants in a reaction, and we have products in a reaction. So the reactants are atoms, well they're molecules typically, that are bonded together. In order to break those bonds, we have to add a bunch of energy to break those bonds. So bond breaking is an endothermic process. If I can spell that, endothermic process. When products form, new bonds are formed, alright? And actually whenever bonds are formed, they typically release energy because their new state has less energy than the state they were starting in, which is usually just as separate atoms. So typically product forming is exothermic. So when we want to find out whether a reaction is endothermic or exothermic, we have to compare the energy that it takes to break the bonds to the energy that's released when the bonds form. And our formula for doing so is simply our reactant bonds minus our products equal the delta H of reaction. Alright, so back in January we saw delta H, and we talked about delta H, but we never talked about where that number comes from. So today we're going to talk about where that number comes from. And we're just going to do one example because the problems are fairly complicated. So we're going to do this, C5H12, which is pentane, and we're going to react it with oxygen. And the problems that would ever be on a test would be a combustion reaction. So it's always going to be oxygen, and we're going to make carbon dioxide, and we're always going to make water. And when we balance this equation, these are always be balanced for you as well. We need 6 waters, because that makes 12 H's, and over here we have 12 H's. And we need 5 carbon dioxides, because we have 5 C's. And if we count up our O's on the right-hand side, we have 10 from carbon dioxide and 6 from water, so that's 16. So we'd put an 8 right here. Okay? So the way this works is you will have everything that's on the right side of the screen in front of you. So these are the energies that are required to break those bonds. So if you have an HH bond, it requires 436.4 kilojoules of energy to break an HH bond. If we have a CC bond, it takes 347 kilojoules per mole to break a CC bond. The opposite's also true, is if these bonds form, it releases that much energy. Okay? So the easiest thing to do on these is really draw out what these look like. So pentane is going to be a C attached to a C, attached to a C, attached to a C, attached to a C. And then we're going to have H's. So we're going to have an H and 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 an H. I'm not going to draw the H's because it's kind of difficult to do so. It just gets cumbersome. And then I have 8 O2s. Alright? So oxygen, when we draw it out, this will always be the same, is a double bond between oxygens. So you don't have to do Lewis structures. I mean, you can do a full Lewis structure, but it ends up being a double bond just like this. And then our carbon dioxide, we have 5 of these. And carbon dioxide is a linear molecule, so we have O double bonded to a C, double bonded to an O, and that's what it looks like Lewis dot structure-wise. And then we also have 6 waters, and waters, you know, are H bonded to an O, bonded to an H, and it's just a bent shape. Know that water's bent, know that water's bent, know that water's bent. Okay, so the way this works is we want to add up all the energy required to break all the bonds on the left-hand side, and then subtract the energy that's released when we make the bonds on the right-hand side. So I'm just going to take my bonds and kind of count how many I have and multiply it by that number. So if I look up here, I have some CC bonds. So I have 1 CC, 2, 3, 4. So I have 4 CC bonds. Okay? And a CC bond, if I come to the left side, I see that a CC bond takes 347 kilojoules of energy to break per mole. Also in my C5H12, if I count all my little CH bonds, I have 12 of those. So I have 12 CH bonds. And if I come over here to the left-hand side, I find a CH bond is 414 kilojoules. Alright, the other things I have over here, I have 8 O double bond O bonds, because I have waters that I need to break. I have 8 of those. And if we come over here to OO, it's right here in red, 498.7 kilojoules per mole. And that is all the energy I have on the left-hand side. Alright, so I'm just going to pull up a calculator. We're going to calculate this out. So I'm going to say, let me just do a little bit, 4, actually we'll do this in parentheses, backspace. So parenthesis 4 times 347, close parentheses, plus 12 times 414, whoops, 414, close parentheses, plus 8 times 498.7, close parentheses, equals, so 10,345.6. 10,345.6 kilojoules is the amount of energy needed to break all the bonds on my reactant side. Then we're going to do something similar on the right-hand side. So if we come over here, I have some C double bond O bonds, which is my carbon dioxide. So I have C double bond O. If we come over here to the left, we find that a C double bond O is right here, 745. However, as there's this little cross and points you to the bottom, the C double bond O bond in CO2 is 799. So over here, that energy is 799. And how many of those do I have? Well, in each molecule, I have one here and one here. So I have 2 for each molecule, and because I have 5 molecules, I have 10 of those bonds. Right, so in water, we have an HO bond. And again, for each water, we have 2 of these. So we have a bond there and a bond there. If I have 6 waters, I really have 12 bonds. And if we come over here to an OH bond, we find that, where is it? It is 460 kilojoules per mole. Joules and kilojoules. So again, we're going to add this up. I'll put my calculator back up. And take 10 at parentheses 10 times 799, close parentheses, plus parentheses 12 times 460, close parentheses, equals, so 13,510. Alright, so finally I'm just going to take 10,345.6, 10,345.6, and subtract 13,510 kilojoules, and my total is going to be 10,345.6 minus 13,510, so negative 3,164.4, negative 3,164.4 kilojoules is the delta H for the reaction, for the combustion of pentane. So again, it's really helpful to draw out the molecules because you want to count how many bonds of each type you have. The great thing is on your homework and test, you will always have combustion reactions. And again, just a reminder, combustion reactions are C and H, and these numbers are something, X and Y. We're always adding oxygen. Oxygen is always a double bond. We're always making carbon dioxide. Carbon dioxide is always 2 double bonds. And we're always making water, which is 2 single bonds to your O's and H's. So anyways, that is bond enthalpy. It's where delta H came from back in January, and now you'll calculate it yourself.